Thank you for the introduction. In my talk, I will tell you about the progress we've done over the past year towards the OpenAI mission. Let me tell you what the OpenAI mission is. It is to ensure that artificial general intelligence, AGI, by which we mean highly autonomous systems which outperform humans at most economically valuable work, benefits all of humanity. In the first part of my presentation, I want to tell you about some of the technical progress that we've made towards simply advancing AI. The first result I want to tell you about is OpenAI 5, which is the neural network that we trained to play Dota at a level that equals that of the strongest players in the world. So Dota is a very large, difficult, popular, real-time strategy game. The main thing about the game Dota is that unlike previous games which were used to test AI algorithms, Dota is closer to the real world. It is a chaotic game where you have partial observability. There are very many actions you can take at any point in time, and the games are very long, lasting for more than an hour, but you have 20,000 actions that you can take during it. Also, significantly, people dedicate their lives to this game. They practice for 20,000 hours, more than 10,000 hours of deliberate practice to get good at it. Another important thing about this game is that it's really popular. It has the largest professional esports scene of any game in the world, and it has the largest prize pool, the largest annual prize pool, which is $40 million. So what we have is that Dota is a very hard game. It is chaotic. It is messy. It is more similar to the real world than previous games that people have tried to apply AI to. And people that play this game, they play this game really well. So it is a hard game. Doing well in this game is not easy. I'm going to show you a small video to give you a taste of how the game looks like.
Oh, no! You can hear it from here. Yeah.
Here you have our bot chasing
fine,
a human player. And this is from August. We were playing against some of the strongest teams in the world. And here, we are chasing.
I'm so sorry.
So here's a bot chasing the human player.
Well, and yeah, here comes the. Didn't do the maths. Yeah, didn't do the maths. OpenAI is beyond math.
Yeah, so we were able to catch the human player in a way that the casters did not expect. So it just shows an example where it can do surprising things. Just to give you a sense you should be able to tell that that's the case from the tone of the voice of the commentators, because the game is pretty complicated to understand, at least at the beginning. So now, I want to tell you how we solve the game. Our entire solution fits into this one slide. And that is very large-scale reinforcement learning. The thing that's novel here is that we show that very large-scale reinforcement learning can solve very hard problems. When our largest scale experiments were such that our bot has accumulated more than 500 years of gameplay experience in one game. The policy that we use to play the game is now consuming as much compute as that of a honeybee brain. The training was done through self-play, where the neural network is playing against a copy of itself. As the neural network gets better, its opponent gets better. So when it's very weak, it has a weak opponent. And when it becomes strong, it has a strong opponent. So it can always improve. And as a result of this, we did not need to use any human data at all. A small amount of reward shaping was necessary as well. It wasn't simply optimizing the win or the lose, but it was also optimizing a few things like its resource accumulation and its short-term wins in fights. So that's it. This is the solution. It's so simple. So where's the science? What's innovative about it? And this is actually a very common theme in deep learning, where a lot of discoveries and breakthroughs do not consist of new algorithms. Instead, they consist of a realization that the old algorithms were more powerful than we thought. And the same is the case here. Before our results, nearly all experts in reinforcement learning believed that reinforcement learning is actually not such a great technology, that it cannot solve hard problems. The only hard problem that's been solved prior to our work on Dota was AlphaGo. But it was using tree search, and so everyone said, well, it's using tree search, so it's really different. It's kind of reinforcement learning, but not really. The normal reinforcement learning is really not that good. But we showed otherwise. We showed that the same story that we've seen with supervised learning also takes place with reinforcement learning. We already know that with supervised learning, if you want to solve some problem, you can probably do it if you collect a large enough labeled data set. And this is why we see all the commercial applications of AI today, because supervised learning works so well. But what we've shown is that the same holds true to reinforcement learning. If there is a problem that you want to solve really badly, even if this problem is very hard, reinforcement learning can succeed if you give it enough experience. The amount of experience required is very high, admittedly. So at least today, on the surface, it may appear that this is only restricted to simulated environments. But this is it. And I want to just give you some cool facts to give you a taste of the scale that was required. We used more than 100,000 CPU cores to generate the experience in parallel. So you got 100,000 CPU cores in parallel and several thousand GPUs running the neural networks for multiple weeks. This was the scale that was required. Another fun fact is that when we were playing in the International in August, when we played close matches against two very strong teams, world-class teams, but then we lost to them, is that the network has not had much, due to the timing of the contest, the network did not have as much time to practice with the new rules. And so it would be very interesting to see what would happen if the same match were to take place simply 2 weeks later. There is one other piece of information I want to tell you, and this is the rate of growth. Let's see. OK, it's too hard. What this plot shows is the improvement in the strength of our bot as a function of time. So here is the interesting thing to note. We started in May. We didn't start in May, but in May, right here, our bot was finally able to beat the team consisting of the strongest Dota players who also happened to work at OpenAI. So this was in May, which is not long ago. Then, in June, we were able to beat a much stronger team, and stronger team still. In July 1st, so that's, I guess, 2 months after May, we were able to beat a semi-pro team. Here, on the y-axis, what we are showing is the MMR, the estimated MMR of the team, which is kind of like an ELO rating. If there is a gap of like 500 MMR, it means that the probability that you're going to win is very high. So every time you have a 500 MMR gap, you're very likely to win. OK. Afterwards, we were able to, in August, we played against these two teams, which are the strongest teams in the world, and we lost. But the matches were very close. And in fact, for the first 30 minutes of the games, it wasn't clear which way the outcome is going to go. So that gives you a sense. So we're talking about, I guess, a 4-month time span. And during those 4 months, the strength of the bot increased extremely rapidly. So that's an interesting fact to think about. It takes a human many more years to become so good. OK, so this concludes my summary of our Dota results. I want to switch to the next cool result, Dactyl. So this is our work on robotics. I'm just going to show you a video of what we did, what we accomplished. We built a system which can control a physical robot. This is not a simulation. This is a real robot reorienting a block made out of wood. So there are no sensors inside the block. It uses vision and sensation to tell where the block is. And what you see at the bottom right is the target orientation. So it's trying to reach a target orientation. And then once it reaches it, it's given a new target. So now it reached it, yep. Now it has a new target. And will it succeed? Of course it will succeed. It just takes it. Yeah, look at it go. It's so cool. So I want to tell you how we did that. Oh yeah, I don't happen to have a video of this, but we also got the same result with a differently shaped object. And it was also pretty easy to do, because our approach doesn't seem to care too much about which object it is. So one of the valid criticisms one could make to our Dota bot is that it required a huge amount of simulated experience. And therefore, you can conclude that, OK, sure, your reinforcement learning works on these simulated environments, which is pretty good. But the real world, you cannot collect this much data. It's just impossible. It's too expensive. It's impractical. So you're never going to be able to solve hard problems like you did in simulation. So we thought, wouldn't it be nice if we could train our system in simulation and deploy it to the real robot? Train in sim, deploy in the real world. And I'm just going to show you how we did that. Because this slide is going to be technical. So if you want to zone out for a few minutes, you can. The next 2, 3 slides are going to be technical. So feel free to not follow. But if you're curious, then pay attention. So why is sim to real hard? Sim to real is hard because the simulation is different from the real robot. Like, imagine you have your block. You don't know the friction of its sides. You don't know its precise size, and you don't know its precise weight. You don't know the precise resistance of the forces on the robot. There is a whole bunch of things you don't know in the simulation. So we had a very simple solution by using an old idea. It is an old idea called domain randomization. The way it works is as follows. If you don't know something, you randomize it. And you request your system to succeed, not just for one size of your block, but for any size. Not just for one value of the friction, but for any friction. You create a robust system which can succeed even if you change the friction, even if you change the weight, even if you change the resistance and all kinds of other attributes. And that was enough. By training our system in simulation to be robust to all those different variations in physics and appearance, it generalized to the physical robot without any training at all on the physical robot. So we did all our training in simulation and no training on the physical robot. And because of domain randomization, this old idea, we've shown that it works. So again, it's very simple. Train in simulation, add a little bit of domain randomization, and deploy it on the real robot. And I just want to tell you one cool fact. The cool fact is that the training code that we used to train in simulation, to achieve in simulation, was the same code which we used to train the system to play Dota. So think about that as well. I find this to be very inspiring. How can it be? How does the algorithm know which problem to solve? It just doesn't seem to care. It says, give me the problem, I'm going to solve it. So this gives you a hint of the generality. OK. So that's good. Now, I want to spend a little bit of time telling you about one more result. This result, in some ways, is technical, but it has the coolest videos. I'm going to go to a technical slide where it's totally fine to pay less attention, unless you're curious, in which case you should pay more attention. So here is the technical part. In reinforcement learning, here is how reinforcement learning works. Here's how it works. It is actually simple. Hear me out. Reinforcement learning works by having your agents try to do different random things. You do something random, and then you see if you like it or not. And if you like it, you do more of that. And this sentence summarizes the essence of reinforcement learning. It also works if you're able to get your feedback. You try to do something, and you see, OK, was that good? Probably. It probably is good. Or maybe it's not good. And on this basis, you learn. Now, where it breaks down is in situations where you don't get the feedback. There is a famous computer game in AI research called Montezuma's Revenge. This game is famous for not having a lot of rewards. The agent needs to do lots of different things before it can get any reward at all. That's how Montezuma's Revenge is like. So this game was famously difficult for reinforcement learning algorithms because you would take your random moves, and you wouldn't get any reward at all. So you couldn't learn because you need the feedback. In reinforcement learning, you do something random, you do something different, you do something new, and you see if you like it. But you need to be able to tell if you like it or not. You need to get the feedback. If you don't get the feedback, you can't learn. And in some environments, in the classic game Montezuma's Revenge, which is really popular in research, you can take lots of random action, and you don't get any feedback at all. No feedback, no learning. So here is the very simple idea that we use to solve this problem. We had a certain way of determining if a state is novel. And if it's a novel, then you get positive feedback. You get rewarded. You're basically saying, seek novelty, avoid boredom. It's not a new idea as well. The thing that is new is that we implemented it without any bugs. We fixed all the bugs in the code. And while it may seem amusing, those bugs are extremely difficult to fix. And in fact, once we fixed all the bugs in our code, we used our code base to re-implement some other existing methods which used similar ideas. And we got better results than they did with their own published work because our implementations had fewer bugs. OK, I'm going to show you the video now. Now that you've heard the theory. So to sum it up in one sentence, I guess 2 sentences, reinforcement learning is the thing you do when you try something new randomly, and then you see if you like it. And if you like it, you do more of that. That's reinforcement learning. The second thing is, when you are in a situation where you just don't get feedback, what do? One idea is you seek novelty and you avoid boredom. Seek novelty, avoid boredom. And if you do those 2 things, cool things will happen. Here it is. So here's the game. Actually, let me just explain the game to you so that you'll have some context of what you're going to see. It's a platform game. So you got this little character jumping around the platform, and it's doing things like collecting keys and collecting coins and collecting a torch. And it needs to move from room to room, and it needs to collect some items in order to unlock some other doors that lead to some other rooms and that kind of stuff. And you'll just see it act. Here it is going through lasers, collecting some coins. Out. It really likes to be close to deadly things, which you may have seen some of this behavior in humans also. OK, so this shows what happens. We basically, in the game Montezuma's Revenge, and this is another visualization of all the different rooms, of all the different rooms in the game, basically our algorithm was able to sometimes visit all of them and pass the first level. And to give you a sense of how big of an advance it is, we have made this convenient plot for you to inspect. So all those different blue points show the performance on the game Montezuma's Revenge. And this is our work. So this is the before, and this is the after. I'm going to show you one more cool video. Mario, another game you've heard. Here, we did something different. We told it, forget about rewards. Forget about winning the game. Let's just see what happens if we tell you, please don't be bored. What will you do if we ask you to please not to be bored? And the answer is quite a lot, it turns out. We're going to show it to you right now. And basically, it learns to not to hate dying. It doesn't like dying because dying is boring. When it dies, it goes back to the beginning of the level or to the beginning of the game, and it's already been there. So why would it want to do that? That just sucks. So it passed the level. It's pretty interesting. And if you notice, you'll see that it doesn't go after the coins because it doesn't know that coins are interesting. It just wants to do cool, new, interesting things. And now it's like it just keeps going, and it just does very oh, it died. That's not good. So it just does sensible things, and it passes more levels, and it seems to be pretty competent. And yeah, it just keeps going. It's not perfect. Oh, that's cool. There's a boss in this level, and you're just going to kill the boss. Let's see. Yeah, so this is the boss, and he just took care of it instantly, no problems. Now, very sadly, it died. But that's what it can do when it's simply been requested to not be bored. This is how not being bored looks like. I want to show you two more videos, a little bit more technical, that gives you an illustration, a more refined, fine-grained illustration of how the boredom avoidance business looks like. So I'm going to show you a video of the game of Pong. The game of Pong looks like this. You've got a little paddle right here, and the paddle has this little ball which is trying to bounce off, so you want to hit the ball, and the ball is going to hit those stones. And what you see here are the rewards, the boredom, the kind of the curiosity-based rewards that the agent gets. Let's see what happens. And you have the little dot which shows the actual rewarded experience right now. So OK, and notice it hit a stone, and it got a huge reward, the spike. So basically, like, yeah, it happens to be interested by the right things. Look, I made a stone disappear. That's really cool. That's the beginning of training. Later in training, when it's already good at not making stones disappear, this is the end of the level. And you see this giant spike. So you can guess what's going to happen. When we pass the level, it's going to be really surprised that you can do that. So look, we're about to pass the level. And yeah, look at this giant reward that it got. So it's just sensible. It's what you'd expect. So to sum it up, in reinforcement learning, the way it works is you do something random, and you see if you like it. But sometimes you may not know if you like it or not. Sometimes the feedback is hard to get. So at the very least, if you try to not be bored, if your feedback is, am I bored, is this new, that's a pretty good objective. And we've implemented it so well, we found the right design choices and the right implementation so that we could achieve these unprecedented results on Montezuma's Revenge and the school Mario video. And hopefully it will be useful in many other applications as well. OK, so this concludes the first part of my presentation. Now I want to go to the second part of my presentation and talk about the OpenAI mission. As I mentioned to you earlier, OpenAI's mission is to ensure that artificial general intelligence, AGI, by which we mean highly autonomous systems that outperform humans at most economically valuable work, benefits all of humanity. That's from the OpenAI Charter. And I want to spend a little bit of time talking to you about this AGI business. What is it exactly? So let's just try to think through the consequences of a system which can outperform humans at most economically valuable work. And because the systems are going to be computer systems, they'll be cheaper to run, so we will be able to generate very massive wealth, which has the potential to end poverty and achieve material abundance, which are nice things. Other nice consequences can be that we will have systems which can automatically generate science and technology. And that will be nice too. We will be able to cure all sorts of diseases which are currently incurable, extend life, and have superhuman healthcare. That will be cool. We could mitigate global warming, clean the oceans, fix the environment. That will be nice as well. Massively improve education and psychological well-being. So those are some of the... This is not by no means an exhaustive list. This is more meant to give you an idea of the ways in which the world will change once such systems will be created. But you can respond by saying, well, sure, of course. Like when you build those systems in like in 500 years or 1,000 years, then these problems will become relevant, and the OpenAI mission will become relevant because no one will have a job. But it's not relevant today, is it? I mean, we are so far from building anything like AGI. We are so far. Why bother? Why even talk about it? And so I think this is a very valid question. And to address this question, in the next part of my presentation, I will simply present to you the progress that we've witnessed over the past 6 years. I'm going to show you some facts. I'm going to show you some curves, essentially. And our conclusion from inspecting this progress is that near-term AGI cannot be ruled out, and it should be taken as a serious possibility. OK, let's review the progress that we've seen in the past 6 years. All of it, 100% of the progress that we've seen is driven by the neural network. The humble neural network, which was invented many decades ago with the backpropagation algorithm, has miraculously been able to overcome year after year barriers which seemed to be insurmountable at this time. And I would like to show you some examples of these barriers being completely destroyed. So, you know, we talk about the deep learning revolution and how it changed everything. One useful thing would be to look at how AI used to be before the deep learning revolution. Here's an example. So what you see here is a demonstration of a vision system which was state-of-the-art from 2005 to maybe 2000, for a few years at least. It's the hog features. They were really popular. And so the interesting thing here is you can see their mistake. You see this little rectangle, and here we have it zoomed in. So the hog feature thinks that this is a car. Why would it think that this is a car? You're smiling, but this was state-of-the-art. It thinks that this is a car because when you give it through, run this little image patch through the hog feature, you get this thing. And this thing does kind of look like a car, and it template matches to a car. So things were pretty bad, and everyone were pessimistic, and it looked like the AI will never work, and the AI venture will remain with us forever. But thankfully, that was not the case. And in 2012, with Jeff Hinton, Alex Krzyzewski, and myself, we were able to show that deep neural networks can do much better than previous approaches. But the thing that's really interesting is what happened afterwards. What happened afterwards is that the speed in which things improved was very high. So this 2012, so this shows performance on the ImageNet dataset, top 5. So we got down to 15%. In 2016, it's got down to 3%. And in 2018, it's less than 2%. So you got this almost exponential reduction in error year after year. Well, that's kind of cool. But it's not the only case where we've seen such examples. Here is machine translation. So in 2014, we've seen the first examples of neural networks being applied to machine translation. And I was involved in making some of that happen. And from 2014 to 2018, we've seen an increase. So just a little bit of context. Accuracy on machine translation is measured with this thing called the BLUE score. You don't need to know what it is. It just has a name, the BLUE score. What matters about it is that the important thing about the BLUE score is that before neural machine translation, it was increasing super slowly. If you were to write a paper which improved your state-of-the-art machine translation by 0.1 blue points. That was a major advance. OK, so this is the performance on a certain mature data set, the WMT English to French. With something like English to French, you can say performance is already pretty solid. There is no way you can improve it much more, is there? And yet, over the past 4 years, we've seen an improvement of 9 blue points in an accelerating way. So that's pretty good, pretty interesting. We've seen a rapidly increasing and even accelerating performance in machine translation. I want to go also through image generation. In 2014, the GAN was introduced. But it wasn't that good in 2014. So it could generate these faces, and it could generate those images. OK. Then in 2015, the DC GAN was introduced. This was done by my colleague at OpenAI, Alec Radford. And it generated those faces, which were higher resolution, but kind of slightly deformed. And you have those images of kind of cool-looking bedrooms, I guess. OK. But then in 2017, you have this. Those images are generated. Every single pixel that you see is output by a neural net. Those are not real people. And in 2018, you have this. So those images are generated by a neural network also. The reason you can tell is that if you start paying attention to this little rocket here, it's, I guess, a space shuttle, you will see that it doesn't make sense. But it will not be easy to see. It will take some effort. So let's go back. Oops. 2014, 2015, 2017, 2018. This is a super rapid increase in performance. In fact, I'll say this. If you were to go back to 2016, the overwhelming majority of machine learning researchers would have been very confident that this would not be achievable. 2 years ago, 3 years ago, it would be even inconceivable to dream that something like this would happen. OK, that's pretty interesting. Next, I want to go to one more area, which is reinforcement learning. So deep reinforcement learning in particular is another area which has experienced extremely rapid increase in performance. In 2013, DeepMind released this paper, which showed how to apply a neural network with reinforcement learning to a computer game. And it was really cool because now you don't have just a neural network which does perception. It also does action. It has perception and action. And that's really cool. But of course, it's just such a simple game. It's not useful or anything, obviously. Then in 2015, we've had a little bit of progress. And now deep reinforcement learning could train these stick figures to run like that, which is cool. It's like maybe one day it will be useful for robotics. Maybe. It looks kind of cool. Then in 2016, we've had AlphaGo. The interesting thing about AlphaGo is that when it happened, the experts were surprised. Many people were really surprised by this because it had such a huge state space, and the planning is so complicated, and it beat all humans. Now, of course, after it happened, people started to say, well, you know, the game of Go, the state space is so small, and the games are so short. But we know this is after the fact, not before. And of course, the belief after that was that, well, OK, fine, you can play those board games, but you can't play some of these harder games, real-time strategy games. There's just no way. The tools aren't powerful enough. And then in 2018, we came out with OpenAI 5, where we've used a very large scale, admittedly, very large scale, in order to play on par with the strongest teams in the world. And then in the same year, about the same time, we've also shown that you can take what you've learned in simulation and apply it to the real world. So this is progress in deep reinforcement learning. And let me just give you a quick recap of what we've seen. This is 2013, 2015. This is state of the art of 2015. 2016, quite a big jump. And then 2018. So it's like this. Deep reinforcement learning has improved extremely rapidly. So that's pretty nice. Or what else? What else is there to show? There is one other hidden dimension, very important dimension that has been a key driving force behind all the results that we've seen, and that is compute. So you need to know two things about compute. The first is that it grew extremely rapidly, and the second is that neural networks can absorb all the compute that you give them. So here is a fun fact. Over the past 6 years, the amount of compute used by the biggest neural network experiments has increased by a factor of 300,000. 6 years, 300,000. This is a lot faster than what we are used to in Moore's law. It's been mostly driven through parallelism. But on the other dimension, which is interesting, is that the neural network algorithms were able to consume all this compute. This is why we've seen all this increase in performance. Our algorithms have barely changed. We've simply developed the skill to apply them at scale and realize what it can do. And so it's also very remarkable, I find, that as we make all these advances, our algorithms barely change. It's just we discover new properties of our algorithms. So what other hidden properties do our algorithms contain which we haven't discovered yet? And nobody knows. But I do believe that we have not yet uncovered all their secrets. Next, I want to show you a little animation to give you a much more visual sense of what 300,000 increase in 5 years means. This animation is going to be similar to some animations you may have seen when you have a picture of. You may have seen some of these animations which try to convey the scale of the universe. When you show like a person, and then you zoom out, and you show the street, then you show the city, then you show like the Earth, then you zoom out some more, you show the moon, then you show the solar system, then you show the galaxies. So you know, that thing. So we did this. We created a video like this, but for compute. And I'm just going to wait. Oh, OK. I want to just show you where to pay attention to. So this is going to be the animation. So you have these columns right here, and they show compute. They show the compute that was required by the different results. And you'll see that only the third row right here, it doesn't go all the way to the end. All the other columns go far beyond the scale of the slide initially. And we're going to zoom out. Now, here, we show the amount of compute required by various classic neural net results from the 90s. And here, we show all the important, a subset of the important results of the past 6 years. And I'm just going to press play, and we're going to begin the zoom out process. And just look at it and just experience the increase in the compute. When you show it on a log scale, it just kind of doesn't feel the same way. So let's do it. All right. So the old results have vanished. You don't see them anymore. And here's the axis. You can see how the axis is zooming out. OK, DQN, the Atari plane neural net, it was pretty small, so that's why it didn't take a lot of compute. The neural net was small. And it's disappeared. You don't see it anymore. OK, let's keep going. OK, dropout. This is a dropout paper. And this is AlexNet. Disappearing. OK, this is the sequence-to-sequence model. You can see it. Yes, you can see the end of that. Deep speech. ResNet, neural architecture search. We'll see that eventually, but just feel it. Look how much we've zoomed out. OK, exception, our 1v1 Dota TI. This is neural machine translation, and look at this. Still going. This is the Dota 5v5 Ti. This actually column is out of date. It's much larger right now. We haven't calculated it. Alpha 0, alpha go 0. So this should give you a visual sense of a very hidden trend that's been going on over the past 6 years, whose visible manifestations were the results that I've shown you. It is really, I find it really almost incredible that no matter how much compute you have, You could just train a bigger neural net on more data, and you will get better performance. I just find it inconceivable. And the other thing which is totally remarkable is that the kind of compute which you need for neural nets is buildable. So that's why we are seeing this progress. Because it's just a neural network. It's in the name, network. So a network of computers. And if it's a bigger network, you're going to have more compute. So that's I find that to be very inspiring and remarkable. And of course, there are some questions, conclusions. So what do we want to conclude from this? Like, it is obvious and unquestionable that very formidable challenges in AI remain. Unsupervised learning, robust classification, reasoning, abstraction, and who knows what else, which we don't know how to do. There are real limits, conceptual limits, which appear to be insurmountable today, just like there were conceptual limits which appeared to be insurmountable in the past. But we've also seen this very strange trend of extremely rapid progress. So we've seen the rapid progress in compute. We've seen the rapid progress in results. And so the question is, what's going to happen? Will this trend continue? How long is it going to continue for? Is it going to slow down or not? And where will it stop? Will it get to AGI? How will you place your bets? And so that's really all I had to say. That while highly uncertain, near-term AGI should really be taken as a serious possibility. And what it means is that we need to think not just about the benefits, but also the risks posed by such technology. Very powerful systems pursuing goals which were misspecified by their creators, very powerful systems misused by malevolent humans, and an economy that's growing extremely rapidly without actually benefiting the quality of life of the humans, which we would wish it benefited to. And this is all I have to say. Thank you very much for your attention.
Now we have time for some question and answer. So we open up to the audience to ask questions. We have a volunteer to bring mic to you.
Thank you, Ilya. Very inspiring content. So AGI is possible, near future, that's what you said, right? Okay, now, if you do not have access to simulation data, and if the physical world is, obtaining training data from physical world is expensive and painful, then how would you apply curiosity model to such space models?
When the simulation is not accessible, and that's the case in most problems, we need to get the data. And one area which I didn't talk much about in this presentation, but it's also very exciting and making very rapid progress, is unsupervised learning. This year is the year of unsupervised learning in language. There have been a sequence of results which showed that when you simply train a language model on natural text and then fine-tune it on different tasks, you get surprisingly good results. We had a blog post about it in June, which showed that you can have one system, one language model fine-tuned to different tasks. It just gets much better performance than all previous systems by a big margin. And then a few months later, Google, in their work on the BERT model, scaled it up, changed the cost function a bit, and got even better results. And basically now we're in a place where if you want to do natural language processing, you must use unsupervised learning. And unsupervised learning has the potential to be the answer to this question. Unsupervised data is cheap, and models are getting large, so they can absorb all this data. And I think this is the direction we'll see things heading.
I have a simple question. we always see the top 5 in classification. Top 1 is not that great so far, 82%, 83% accuracy, and it hasn't really improved much in the last few years. It's, I just wanted to know if there are classification networks that actually give you higher accuracy for top 1, because top 5 is a metric, top 1 is the real thing.
Yeah, I think the question of top 1 is very good. I think one issue with these, every data set has an unreachable error rate, which, for example, is a function of the ambiguity in the labels. So I think the best way to do it is to have a panel of humans try to classify each image. And that will tell us the accuracy, the best attainable accuracy on the data set. And I think that we'll probably find is that something like the best attainable accuracy on ImageNet top 1, my guess would be maybe 7% or something like this, maybe even 10. But I'm not sure. Don't quote me on this. I think this is the kind of prediction which is very easy to be embarrassed about later. I also think that top 1 is now 85%, I believe.
Okay, so maybe there's a new result, because I have seen 82, 83% with Inception v4.
Yeah, I mean, I haven't been following it very closely, but I think I mean, 80. I also don't have a good intuitive sense of what 84% top 1 means, like what's the nature of the mistakes and how close it is to being the highest achievable accuracy. I just don't know the answer to that.
Right. The other question I have is that we have lower accuracy for object detection than the classification networks, and I'm not sure even it goes to 80%. You know, I mean, these are real applications, for example.
Yeah, so I think this is a very good point. And I would expect the same kind of unsupervised learning that's been helping out with NLP within not too long of a time to help with vision as well. And I expect that to be a significant improvement. But the models that will be required for this will be far larger.
Hey, Ilya, thank you for the talk. It's very inspiring. So I'm from JP Morgan, so working on AI in finance. So finance is all about decision making, long-term, short-term. Could you maybe share some of your thoughts about how to use reinforcement learning in finance usage?
So, I mean, I think the best, so first of all, I should preface my answer by saying that I'm not a finance expert by any means. I don't have any experience whatsoever with this domain. I would guess if you want to do some kind of, if you want to decide if you want to buy something or sell something or authorize some kind of decision, you want to be able to predict the consequences of a decision that you would have made as accurately as possible. So if you have already a system which is making a lot of decisions, you could train potentially a very large neural net that will try to predict the consequences of those decisions. And I think for something like trading, I think it can work pretty well. For something like authorizing loans, you have to be careful with things like bias. But in general, I mean, I think you can, in my opinion, there should be a huge number of places you could apply big neural nets in finance and get very good outcomes from doing that.
Great. Let's thank Ilya for his talk.
Thank you.
Thank you. Our next session